All right, welcome to Chapter 5. In Chapter 5, we're going to introduce to you your very first chemical reaction, or your very first kind of chemical reaction. All right, this kind of chemical reaction is combining two chemicals together, all right, that are dissolved in water, Now, when I dissolve a chemical in water, do you remember that you have, for example, if I have this chemical here, do you know the name of that chemical? Ag is silver. That's right. And what's the NO3? Do you remember?
That's the nitrate.
That's right. Silver nitrate. Very good.
Okay.
So, if I want to show that it's a solid, what do I put down here?
S.
Or if it's a liquid?
L.
And what if it's a gas?
G.
But what if it's dissolved in liquid, or dissolved in water? Do you remember that?
That's aqueous.
That's right. I put a little AQ down there for aqueous. Okay? So, why do chemical reactions occur in water? Well, because for a chemical reaction to occur, the two components that you're going to want to react, the reactants, have to actually collide. They have to touch. And for as much as we'd like to think about a solid, finely ground solid material like flour or something being well dispersed, it's not. It's not well dispersed. And if you mix two solids together, there's not very much of there's a limited amount of interaction that those two solids can actually have. Really, to get chemistry to done well, chemicals need to be completely separate from all their entities, their neighboring entities. Like when you dissolve something in water, everything dissolves and spreads out evenly, like in a homogeneous solution, right? So we're going to talk about chemistry in aqueous solutions to start off with. Okay? And to do that, first we have to come up or understand a few of the concepts or the vocabulary that describe a solution. Now, a solution is a homogeneous mixture where there's two compounds or two materials, right? Usually we think of it as water dissolving something, so like salt dissolved in water, and that's an example of a solution. In that solution, the solvent would be the water, and the solute would be the thing that we dissolve into the water. Okay? So, another example, I have a pile of material here. It's on a plate. I'm going to put it into a beaker of water, right? This is my water. It's my solvent, okay? My solvent, water, for example. Usually we're talking about water. And the chemical that I want to put into my solvent is my solute, okay? So I got my solute and my solvent. Okay. After we have the solute in the solution, in the solvent to form the solution, right? Then we can talk about what we call the concentration, how much of the solute is actually dissolved. And we might be familiar with the word dilute or dilute, right? That just means that there's hardly any solute. So like here I can see I'm putting in a chemical into this water and the chemical is dissolving, all right? What happens if you put too much of, let's say this is salt, for example. If you were to keep putting more and more salt, eventually the salt would not dissolve. Eventually it would just start to kind of gather at the bottom of the container, right? And in that situation, you would say that the solution is concentrated or saturated, all right, with our solute, okay? All right. And another word, we talked about the word saturated, right? No more solute can dissolve. Solubility is kind of a measurement of how much solute can dissolve, and the solubility of a salt or a molecular compound, any compound in water, varies from compound to compound, all right? Unsaturated, what do you think unsaturated means?
More solute can go in the solution.
That's right. More solute can go in the solution. Supersaturated. Supersaturation can occur because we can change the temperature of the solutions and change how much solute can be dissolved into the solvent. What do you think? Do you think that when you put a solute into solution and then you cool that solution down, how is that going to change the solubility of the salt or the compound that you have in there?
I think the colder the solution, the less material will dissolve in it.
That's right. That's right. And maybe you put sugar in cereal before, and when the milk is cold, you get a pile of sugar on the bottom because it doesn't dissolve very well, right? That's sort of an experience. Okay. Now, not all of our ionic compounds will dissolve in water. Not all will dissolve in water. Or in other words, they're not soluble. They're not all soluble in water. And so what we have are what we call solubility rules. Solubility rules. These solubility rules help us know whether a compound is soluble in water. And the solubility rules are available to you on the back of your periodic table. Let me bring up the periodic table here, or here's the back of your periodic table. You have the solubility rules right there, okay? So we'll be using those solubility rules to know whether or not a compound is soluble in water, okay? So let's do some examples here. Get those solubility rules out. They're on the other side of your periodic table. Get them out and we'll take a look at them, okay? And try to answer these questions. Will these chemicals be soluble in water? All right, so look through your solubility rules and see what you can find.
I don't see. Okay, so Rule 6 talks about carbonates, and that's calcium carbonate. Rule 6 says that carbonates are not soluble except...
Yeah, there's some excepts, right? A lot of the rules have excepts on them, so you have to read through them all the way.
Yeah, so carbonate's not soluble with calcium, so calcium carbonate is not soluble.
Okay, very good. It's not soluble, calcium carbonate. How about iron chloride?
Rule 3, chloride. Yeah, so that's soluble.
That's right. There are some exceptions, but iron is not one of the exceptions. So chlorides are generally soluble. So here, we got another one. Is that one soluble too? Lead chloride?
Yeah, I think so. Let me read Rule 3. Except, oh no, lead is one of the exceptions.
That's right. Lead is one of the exceptions. So lead chloride is not going to be soluble. Okay. Also, in terms of solubility, we can answer these types of questions where we look and see what the solubility of a compound is in solution. Here we have information about 39 grams of sodium chloride being able to dissolve in 100 grams of water, and they tell us the temperature. We don't talk about or receive information with respect to the change in solubility at different temperatures in this class, but that information is out there. Now they're asking if we put 10 grams of sodium chloride in 50 grams of water, at this temperature, is the solution saturated, unsaturated, or supersaturated, or none of these? What do you think?
Well, with 50 grams, you should be able to get more than 10 because you got 39 grams of the 100. So half of 39, that's 19 and a half. That's more than 10. So I would say we're unsaturated.
That's right. Very good. Unsaturated. Okay. So, ionic compounds. We've learned a little bit about ionic compounds, and we know, hopefully by now, like this video has shown us in the past, we know that ionic compounds reside in three-dimensional lattices. Three-dimensional lattices, right? So this is an example of sodium chloride here. Our sodium ions and our chloride ions are all in a close cubic packed scenario here, where we have each chloride ion here has 6 neighbors, one in front, one in back, one right, one left, one top, and one bottom. This one's on the edge, so it doesn't, but you can see how it would. Same with the sodium ions, 6 neighboring chloride ions. But when you put this into water, It dissolves. Now, what's happening at the molecular level when we dissolve something? Well, when an ionic compound goes into water and dissolves, what's happening is the water molecules are surrounding the different ions and pulling them away from each other. Whoops. So this is the same thing that is happening in molecular compounds, but in molecular compounds, the water molecules are surrounding the whole molecule. But in the ionic compounds, the water molecules are surrounding just the ionic compound, So you have the ionic compound being surrounded, and just the ions in the ionic compound. So you have the ion being surrounded by the water molecules, and let's keep watching. The water molecules, here it's the hydrogen ends surrounding the chloride, and we'll talk about why in the future, but essentially the hydrogen ends have more of a positive charge on the water molecules. Here the negatively charged oxygens are surrounding the sodium ion and pulling it away because it's positively charged. The oxygens have a slight negative charge. So this whole process continues, and what we have is not just dissolving, but something special, which we call dissociation, which is the ions separating from each other. So when ionic compounds are dissolved in water, they separate from each other. And these separated ions then act as electrolytes. They result in conductivity in a solution. We talked about that before, right? So we can call compounds that do dissolve in water, another name for them, or ionic compounds that do dissolve in water, can be called electrolytes because they produce electrolytes. Electrolytes is just a fancy word for ions. Okay? All right. So, again, like we said, molecular compounds, they do the same thing in terms of the molecules being separated one by one when you dissolve them in water, but we don't get any ionic charge. There's no charge because there's no ions in the molecular compound. Okay? And like we said, you get conductivity when a salt, now I hope you've realized that the word salt is used in chemistry for any ionic compound. So when you take an ionic compound, if you take a salt and you dissolve it into water, you will get conductivity. Or in other words, electricity can pass through the water, the solution that you formed when it has an ionic compound. And we call this kind of a compound that can dissolve well in water a strong electrolyte. Strong means that it completely, 100%, dissociates into ions when placed into solution. Now, weak electrolytes exist, and we won't talk about those for a bit, but basically, they're compounds that dissolve momentarily, but then go right back. So at any one moment of time, there's only a relatively small amount of those, the chemical ionized. And then non-electrolytes, and examples of non-electrolytes are like sugar, right? Sugar can dissolve, but it doesn't ionize when it's in solution. Okay. Because our ionic compounds dissociate into, ions when placed in water, right, our soluble ones, we can write what's called an ionic equation. And that's essentially taking the chemical reaction, all right? So here's a chemical reaction where we have sodium sulfate going to sodium ions and sulfate ions. We can take chemical reactions and show them not as sodium sulfate in water, but as the ions that exist when that chemical is in solution. Okay? Now, to practice this or to think about it, what we essentially need to be able to do is anytime we see an ionic compound, we need to recognize that if that's dissolved in water, it's going to break into its ions. So we need to be able to look at ionic compounds, see the ions, see the number of the ions, the charge on the ions, and be able to write them down. Okay? So let's take these compounds here, and let's see if we can write down the ions that will that actually exist when these given compounds are dissociated into water. All right. So what are the two ions in ionic compounds? Cation and anion. Cation is what? Positive or negative charge?
Positive.
That's right. Cation is positive charge. Anion is our negative charge then.
I remember because the joke.
Ah, good. I'm glad you remember because the joke.
Yeah, it wasn't a good joke, though. You should think of a better one.
Well, okay. All right. I'll work on that. Okay, so ionic compounds always have cations and anions. And we always want to make sure we get the right charge on the ions, and we also want to make sure we have the right number of them. So, like before in previous classes, we can tell how many sodium atoms there are in this thing, right? How many sodium atoms? What is this thing? Do you know?
Sodium, let me see. Do you have the polyatomic ion chart?
Yes. Let me pull up the polyatomic ion chart here. Okay. You see it there?
Oh, there it is. Phosphate. Sodium phosphate.
Very good. Sodium phosphate. So we have sodium ions and phosphate ions. And how many of each do we have?
3 sodiums.
That's right. So if I write down something like this, 3 sodiums, okay, and 1 phosphate, that's almost there. What am I missing?
The charges.
Yeah, you need to have the charges. Do you know what the charge on the sodium ion is?
Where's it at on the periodic table?
Let's bring up the periodic table and take a look-see-loo. Here it is over here.
Okay, so it's a +1 charge.
That's right, +1 charge. So 3 sodiums with a +1 charge. And the phosphate, do you remember? Did you see on the polyatomic ion chart what it was?
Yeah, I forgot.
All right, let me bring it up here again.
-3. It's -3 charge.
Okay, very good. So that is what we're going to have, and we can put the plus there as if it's a reaction, right? Or as these things are combining together or whatever. So we have 3 sodium ions and 1 phosphate ion. All right, so that's how we write the dissociation of these ionic compounds. Okay, so what do you think? What is this next compound called?
Is that aluminum?
That's right, aluminum. SO4.
Let me look on the chart here. I got my chart with me today.
Oh, good. You brought your chart. Excellent. So look on it and try to find out what it is.
Sulfate.
That's right. Aluminum sulfate. Aluminum sulfate. So how many aluminum ions?
2.
How many sulfate ions?
3.
Okay, 3 sulfate ions. What's the charge on the sulfate ion?
Chart says it's a -2.
That's right. So there's 3 of the sulfate ions with -2 charge. Do you know the charge on the aluminum ion?
I have my periodic table, but it's kind of a weird one. I'm not exactly sure. Aluminum's way over there.
Here, let me bring up the periodic table. So yeah, aluminum's over here, but you can always just count. 13 electrons here is how many aluminum would have. And remember, it wants to have one of these numbers. So it's going to have to either gain 1, 2, 3, 4, 5. That's a lot of electrons. Or it can lose 3. So aluminum is going to form a +3 charge. And it's a cation also. So that's another way to remember that. It's, in this case, for sure going to be a positive charge. So aluminum has a +3 charge. Okay. So another way that we could have remembered that is we could have taken aluminum sulfate, the way that it's written here. Okay. And we could have done the reverse with the crisscross rule, right? To remember that aluminum has the +3 charge and the sulfate has the -2 charge.
Oh, yeah, that's good. That's good. That's a good one.
Yeah. Okay, so very good. Next, what's next?
Calcium chloride. Chloride has a -1. There's 2 of them. I don't even need to look at the periodic table. Calcium must be a +2. So calcium with a +2 charge, and then chloride with 2 chlorides with a minus charge.
Very good. So we're seeing the ions that are in this ionic compound, and we're writing them down. How about this one? What's that?
Calcium, I don't know. Let me look at my table here.
Polyatomic chart?
Yeah. Permanganate?
Permanganate. Permanganate.
Permanganate.
Yeah, calcium permanganate. What's the charge on the calcium?
Do you have your periodic table there?
Yeah, here you go.
Okay, +2. So manganate, I don't even have to look at the chart. I know that if calcium's +2 and there's 2 permanganates to balance it, the permanganate must be a -1. So there's 2 of the permanganates with a -1.
Very good. Excellent job. All right. Now, another question. Which of the following would not be expected to produce chloride ion when dissolved? Okay, so we're dissolving these, right?
So which one would not make the chloride ion?
Yeah.
Sodium chloride for sure would make the chloride ion. Lithium chloride. PCl3. What's P?
Phosphorus.
Phosphorus chloride.
Well, here's a hint. Phosphorus chloride is not the name of that compound.
It's not?
No.
Is P phosphorus?
Yeah, but here, let me bring up the periodic table and show you why. Here's phosphorus right here.
Oh. So phosphorus is a non-metal. So it's phosphorus trichloride. You use the mono, di, and tri when you're naming stuff, if it's a molecular compound. Because phosphorus is a non-metal, phosphorus chloride is a molecular compound, we have to, it won't ionize. It won't ionize when it's in solution.
That's right. That's right. So that's how we know that that will not produce any chloride ions when placed in solution. How many ions form on the dissociation of sodium phosphate?
Well, we get sodium ions and phosphate ions. So 2.
2?
4. What's it? Oh, I think it's talking about 3 sodium ions and 1 phosphate ion.
That's right. It didn't say how many different kinds of ions. It said how many total. So we have 3 sodium ions and 1 phosphate ion. And that's important because as you dissolve an ionic compound in solution and ions result, the conductivity of that solution and other, like the boiling point, the melting point, different things are altered by the number of ions. So we have to make sure that we can recognize how many ions. Good. How about this one? How many ions form on the dissociation of this compound?
5.
Very good. 5 ions. All right. So we can get a chemical equation like this provided to us, and we can break it up into what we call an ionic equation. An ionic equation. And when we break it up into the ionic equation, we do what we were just doing. Everything that's soluble, and, we have a couple ways we can determine whether it's soluble or not. We can use our solubility rules, right? We can always use our solubility rules and look and see if whether an ionic compound is soluble. But we can also, if an equation is provided for us like this, then anything that's indicated as aqueous, it will be soluble, right? So, if I want to write what's called the ionic equation for this, I just take what's soluble, this compound. Do you know the name of this compound?
Ag is silver, NO3, let me look. Nitrate, silver nitrate. That's potassium chloride. That must be silver chloride and potassium nitrate.
Very good, very good. So we have all of these compounds, but silver chloride you see as a solid. So in the ionic equation, or when it's in water, it's not going to be separated into ions. So silver nitrate would be written as silver ions and nitrate ions, potassium chloride, potassium ions and chloride ions. Silver chloride again is together. Potassium ions and nitrate ions are separate. Okay? And then we also have what's called the net ionic equation. And the net ionic equation takes out any spectator ions, anything that isn't doing anything in the chemistry. So you see in this equation, you start off with some nitrates and some potassium ions in solution. And over here, the potassium ion is exactly the same, hasn't changed. And the nitrate ion is exactly the same. So the potassium and the nitrate haven't done any chemistry. There's no change, okay? So we can get the net ionic equation by getting rid of the spectator ions. And what's left is the chemistry, the net ionic equation. Now, let me go over this one more time really quick. What this equation is saying here, what it's actually saying that occurred is I have a solution of silver nitrate, right? And I have a solution of potassium chloride, all right? And those are both in solution, so that's why it says aqueous down there, right? They're both in solution. And then I mix them together. So essentially what I'm doing is I'm taking all of those individual ions, mixing them together, and what happens is some of the ions find each other and form something that is insoluble, right? We can look at our solubility rules and see why silver chloride is insoluble, right? Chlorides are soluble, except for the exceptions, and silver is one of them. Okay? So, if we then, when we want to write our ionic equations, we just look for stuff that's aqueous or strong electrolytes. We break it up into ions. And now, you're not always going to do this in life when you're looking at an equation, but your mind must remember that if you see an ionic compound and it says aqueous, then it's ions. It's not its little coupled molecular form, right? That's not the way ionic compounds roll. Okay, so here's another example. Lead nitrate dissolved in this solution, potassium iodide dissolved in that solution. We think in our minds lead ions and nitrate ions. Here we think potassium ions and iodide ions. But when we combine them together, we make orange juice. Not really, not orange juice, right? But an orange material precipitates out, we say. And it is lead iodide. It's solid, so it's not going to dissolve. So it's going to be little tiny particulates floating around. All right. Here's another example. One solution, mercury chloride, so start over. Mercury, sodium iodide, mercury nitrate on the left, sodium iodide on, start over. Sodium iodide on the right, mercury nitrate on the left. I might have mixed those up. Anyway, they're both solutions, both aqueous. And now when we combine them together, right, precipitate, that's a powder. That's actually a solid floating around. And if you were to wait, it would gradually collect on the bottom of the flask. Okay? So that's what's occurring when we see this sort of a reaction. Right? Two aqueous solutions coming together and forming a solid. Okay, so can you write the ionic equation for each of these reactions? Let's write the ionic equation. All right, we got BaCl2. Do you know what the name of that compound is?
Barium chloride.
Barium chloride, very good. How about this one here?
Lead nitrate.
Very good, but we want to make sure we call this lead some number to help people know what the charge is on the lead. Do you know what the charge is on the lead here?
Can I see the periodic table?
Yes. It's not going to help because lead's over here. It's what we call a post-transition metal. And so we can't really use its location to predict what its ion is. Only our first two columns really can predict the ions. So knowing where the lead ion is just isn't going to be helpful for us. What we need to do is look at something else. What else can we look at?
Oh, the nitrate ion. If you look at the nitrate ion, you see it's a -1. There's 2 of them for every lead. Therefore, the lead must be +2. So that's lead 2 nitrate. The 2 tells me what the charge is on the lead.
Very good. Lead 2 nitrate. All right. Lead chloride, solids, not going to separate. And what's this thing here?
Barium nitrate.
Very good. So I told you what to do with a dead chemist, right?
Well, I don't know.
You bury him, right?
That is another bad joke.
Well, sorry about that, but that's the jokes, right? You got to roll with them.
Let's get back to the chemistry.
Okay, so what's next?
I have to write down the ionic equation. So I got it. You write a barium ion, 2 chloride ions, lead ion, yeah, like that.
Lead ion, nitrate ion, lead chloride stays together, right? Barium ion, and then the 2 nitrate ions. Got to make sure you got the appropriate number of ions, 2 chloride ions. We don't put Cl2 down here, right? Because this Cl2 means that there's 2 chloride ions with the barium ion. All right. Let's see if the folks at home can do this bottom one here. 2 seconds, and I'm going to show it to you. 1, 2, push pause if you need more time. Okay, so there it is, the ionic equation. Now, if our ionic equation has spectator ions, we can get rid of the spectator ions and form the net ionic equation. So, identify the spectator ions in this, if you would, Fred.
Okay, the spectator ions don't change from left to right, correct?
That's right, they're the same.
So the nitrate and the potassium ion are the same.
That's right. Those are our spectator ions, so we get our net ionic equation. That's pretty straightforward. So I'll leave these last two for the folks at home. 2 seconds, and then I'll show you the answers. Push pause, finish them up. 1, 2. Okay, very good. So the net ionic equation gets rid of the spectator ions, and what's left is the chemistry, what actually is occurring, changing. All right, now I get to introduce to you a new kind of compound, And to introduce to you this new kind of compound, I want to kind of work from our diagram that we talked about a long time ago, okay? If I wanted to make a diagram of all the compounds that we're aware of, all the compounds, okay? So in here contains all of the compounds that we're aware of, okay? And what kinds of compounds do we know?
Ionic compounds.
That's right, we know ionic compounds. And, you know, the definition of ionic compounds, compounds made of ions, which is a boring definition because, you know, it's kind of self-explanatory. But we can recognize ionic compounds generally because they have metals in them. But ammonium is an ion that we're becoming familiar with. So contain metals usually, and that's a good way to kind of to recognize an ionic compound. And our other one that doesn't contain metals, no metals, what do we call those?
Molecular compounds.
That's right, molecular compounds. All right, so we have molecular compounds. Now, molecular compounds don't have metals in them. They don't ionize when you put them into solution. They don't dissociate, right? They don't dissociate when you put them into solution. However, if we zoom in really close in here, I'm going to introduce to you a new group of compounds. And it's in the molecules, within the molecules, there are some molecular compounds which do ionize or dissociate. And these compounds are called acids. Acids. All right? Acids. So an acid is a molecular compound that will actually dissociate when it's placed in water. Now, the reason why it can do this is because the ion is the hydrogen ion. Remember how hydrogen is an exception to the rule. However, molecules that contain the hydrogen ion will dissociate, at least to some degree, when placed in water. Okay? So, acids are molecular compounds that dissociate because they contain the hydrogen ion. And so we draw this dissociation. See this part right here, HCl? It's dissociating into the H plus ion and the chloride ion. And it's an acid because it contains hydrogen there in the beginning and because it dissociates and releases the hydrogen ion. So an acid releases the hydrogen ion. Now I have to tell you a few other names for this hydrogen ion. The hydrogen ion can also be called the hydronium ion. And if you look on your list of polyatomic ions, it's in that list of polyatomic ions at the top there with ammonium ion, hydronium ion. Now, we never see a compound that contains the hydronium ion, right? We don't ever form any ionic compounds with it. But what that is, what the hydronium ion is representing, is basically the H plus ion, which is surrounded by water molecules, okay? And it will attach to different water molecules as it bounces around the solution. But it can move fast, you know, it's moving fast, so it's never really on one molecule. It's just bouncing around. So, some people like to see the dissociation where you have, like we've drawn, HCl going to the chloride ion, but others like to see it like this, where we have, well, I'll just show what we have drawn here, okay? HCl combining with water to form our hydronium ion and the chloride ion. You need to be familiar with both. I think that this one here is just as effective HCl and less complicated, so I prefer this one significantly over the other one. But they both represent the same thing. Let's look at our little diagram here. HCl interacting with water. The hydrogen ion is going with the water molecule to form this H3O ion and leaving behind the chloride ion. We have, just like we had strong electrolytes, compounds that you put into water and they ionize, dissociate, right? And we also have weak electrolytes. Well, we have strong acids. Now, strong acids doesn't mean this is the kind that's going to burn the Joker, whatever, right? Or burn through your house. That's not what we're talking about when we talk about strength. Strong acids are acids that completely dissociate, whereas weak acids, they don't completely dissociate. So here's an example of a weak acid down here. It's called acetic acid. It's the acid in vinegar, right? And we have about 5% acetic acid in vinegar, and we drink it, and we seem to be okay. So it dissociates into the H plus ion and what's left, which is the acetate ion. Look on your polyatomic ion chart, and you'll see the acetate ion right there, right? Acetate ion. And that's where it gets its name. Acetate goes to ate, goes to ic, so it's acetic acid. So to show that acetic acid is a weak acid, we put a second arrow here, a second arrow, to show that this hydrogen ion and this acetate ion will come back together and go back here. So right now we separate our acids into either strong or weak, and we help indicate to people what the strong acid and what the weak acid is based on the number of arrows. However, we also want to begin to memorize our 7 strong acids. And I would suggest that you write these strong acids on your periodic table. Somewhere on the periodic table, write down the strong acids, okay? I'm going to write them down here for you. HCl, HBr, HI, so hydrochloric acid, hydrobromic acid, hydroiodic acid. Whoops, no plus sign there. HNO3, nitric acid, H2SO4, sulfuric acid. And you probably have heard of these and not even known it before. HClO4, perchloric acid, and HClO3, chloric acid. So we got 1, 2, 3, 4, 5, 6, 7. Write those down on your periodic table because those are our 7 strong acids. And how do we know they're strong? Because I told you so. Okay. Now, we'll talk about in later classes, not in this class, but we'll talk about how we can kind of distinguish between the strength of acids, that sort of thing. But for now, we just tell you the list of strong acids, and we need to be aware of that list. Now, a base. A base is a compound that, like an acid, you put an acid in water and the hydrogen ion results. A base you put into water, and not the hydrogen ion, but the hydroxide ion, which is the other half of the water molecule. Water, H2O, right? You can think of it as kind of ionizing into H plus and OH minus, right? This is oxygen with 2 hydrogens on it. And if a hydrogen ion, H plus, leaves, then you get an oxygen with a hydrogen left behind with a minus charge on it, right? So that is what is occurring with, well, that's what, when you have an acid, it's a chemical that releases this half of the hydrogen or water molecule, and you have a base, it's a chemical that releases that half, the hydroxide ion portion. Okay? Sometimes it's released, sometimes it just results. And I'll tell you what that means in the future. But many nitrogen compounds are bases, but they don't have hydroxide ion on them. So what they do is they interact with water molecules by pulling a hydrogen off. See how the B here interacts with the water, pulls the hydrogen off, and what's left behind is the hydroxide ion because the water molecule has one of its hydrogens pulled off. And so this base, right, works not by containing a hydroxide ion and releasing it, but by resulting in the hydroxide ion by removing a hydrogen from water. These bases And those are weak bases. Strong bases are just ionic compounds that contain the hydroxide ion. So we can look at our solubility rules for ionic compounds that contain the hydroxide ion, that are soluble, right? All metal hydroxides and metal oxides are insoluble, except a small exception, small group. So in general, strong bases, there's only a handful of strong bases, and the way strong bases work, again, is they're a chemical that dissociates into the hydroxide ion and its counter ion. Okay, so here it is again, our list of strong acids, and we want to recognize again, strong means not its potency necessarily, but the degree of dissociation. Strong acids, strong electrolytes, strong bases, always about the degree of dissociation. All right, so here's a little cartoon here. HCl interacting with water. Because it's a strong acid, all of the HCl dissociates and you get H3O plus the hydronium ion, and we get the chloride ion. All right. So I've told you that this can also be written, HCl, right? Or the dissociation of HCl can also be written as simply this, right? HCl, H plus, and the chloride ion, right? And I want to examine this just from one more perspective, okay? Let's think about that hydrogen ion for a second. If I have that hydrogen ion, and if I start with just a hydrogen atom, okay? Here's a hydrogen atom. Let's draw it real quick. Down here, I'm going to draw it. How many protons does the hydrogen atom have?
1 proton.
Very good, 1 proton. How about electrons? How many electrons?
1 electron.
Very good, 1 electron. All right, now if I have a H plus ion, how many protons does it have?
Still has 1 proton.
Very good. How many electron?
Has 2 now because the plus.
The plus means it gained an electron?
Oh, no. Plus means that it has more protons than electrons, so it must have lost 1.
That's right, it lost an electron. So the hydrogen ion is just the proton, just like that. All right? So you'll hear me and others call a hydrogen ion either the hydrogen ion, the hydronium ion, or you'll also hear it just calling it a proton, because that's all it is it's just a proton if it's just H plus. Okay? So 3 different names that we have for the hydrogen ion. Now, let's look at the dissociation here of a weak acid. Here's a weak acid. This is also acetic acid, slightly different chemical formula. But this weak acid interacts with water, and because it's a weak acid, only a very small amount actually dissociates, right? Really about 1 in 1,000, about 1 in 10,000 dissociate. And then, once it's dissociated, they'll find each other and go right back. But in the process of going back, there's another one that's going to be dissociating all the time. So at any one point in time, you have some that's dissociated, only a small fraction though. So we add on a second arrow to show that this reaction is going back and forth. And we say that this is in what we call equilibrium. All right. So what do you think? If you put a strong acid into water, will the solution become conductive?
Yeah, because you said strong acids completely dissociate.
That's right. How about a weak acid?
No, it won't.
That's right. It doesn't become conductive. It might become a little.
Yeah, just a little.
Right, a little, because it conducts or makes some ions, but not a ton. How about a weak base?
Weak base? I don't know.
Well, let's look. What happens when we put a weak base in? Now, remember, a weak base, strong base, good example, another example here, sodium hydroxide, example of a strong base, because it has the hydroxide ion, and you put it into water. Is sodium hydroxide soluble? It's an ionic compound. Does it dissolve? Does it dissociate when you put it into water?
Do you have your rules?
Yeah, let's bring up our solubility rules here.
Sodium. Well, yeah, because sodium is group 1A, and number 1 says all sodium ions, all group 1A are soluble.
That's right. Very good. So we get sodium ion and the hydroxide ion. So that's a strong base. You put it into solution and the hydroxide ion results. Now remember, a weak base does things differently, right? A weak base, which we can represent just as B for now. Well, actually, I'm gonna represent not as B. I'm gonna represent it as like in problems. Usually, it'll have something like CH3NH2. Right? Usually, it's this weak base is something that contains nitrogen, like nitrogenous bases they call, right? Contains nitrogen, and then it, like the base we saw before, interacts with water, right? Interacts with water. And the result is the base produces the hydroxide ion still, right? But the way that it does it is by removing a hydrogen. So the base takes a hydrogen and that positive charge with it and releases the hydroxide ion. So in this case, the CH3, and we show the base going onto the nitrogen and form the NH3 plus ion. All right. So our strong base works by simply dissociating. Our weak base works by pulling a proton off of water and resulting in the hydroxide ion. And both of these strong base scenarios, or any strong base scenario, will always be in equilibrium. So there's only going to be a small amount of our base dissociated. Therefore, again, maybe a little glow, but not much conductivity in that sort of a solution. Okay, so a weak electrolyte. Let's talk about naming acids now. Let's talk about naming acids. If I'm going to name an acid, I have to look at, I remember two things. One, some acids are binary acids. Binary acid means it has hydrogen and only one other kind of element, all right? Like HCl. There's a hydrogen and one other kind of element, okay? H2S, hydrogen and one other kind of element. Now, there's more than one hydrogen here, but there's only two kinds of elements. Acids that only contain two kinds of elements are called binary acids. Binary acids. And they're named following what I call the hydroblankic model. Hydroblankic. Or in other words, HCl, hydrogen chloride before it's dissolved in water, but as soon as you dissolve it in water, it becomes hydrochloric acid. Now, some of you might have heard of hydrochloric acid before and already know that HCl is hydrochloric acid. And that's good, because if you know that, then you can always use that as your model for naming binary acids. If you don't know it, memorize it from now on, because then it will, again, serve as a model for naming binary acids. So binary acids are named following the hydroblankic model, where the blank is filled in with the first part of that, the element that hydrogen is with. Acids that contain oxygen, oxoacids, are named differently. They're named differently. They're not named following this hydroblankic model. That's only binary acids. They're named by taking the polyatomic ion that they contain. And that's what oxoacids are, is they're always polyatomic ions with a hydrogen in front. Okay? So and that makes sense because these are basically compounds that can ionize in water, so they have to be ionized ions once they're dissolved, right? So that's either polyatomic ions or monatomic ions. So polyatomic ion, the name of the polyatomic ion that is used to form the acid, and you can look at our list of polyatomic ions, you can look at that list and see the charge on here. And whatever the charge is, that's the number of hydrogens that are going to go. So sulfide ion, -2 charge, you just put 2 hydrogens on it, and that will be the acid, right? And so the way that we name it is based on the name of the polyatomic ion. So the polyatomic ion chart is necessary for naming oxoacids. You look at the name, this is the nitrate ion, and if it ends in 8, then the acid ends in ic. 8 goes to ic. If it ends in ite, for this instance the chlorite ion, ite goes to us. So this would be chlorous acid. So this is something that you tell yourself every morning when you wake up. 8 goes to ich, ite goes to us. 8 goes to ich, ite goes to us. You want to try it?
Yes, I do. Thanks for asking. 8 goes to ich, ite goes to us. 8 goes to ich, ite goes to us.
Very good, very good. So let's try to name some acids. Which of the following is not named following the hydroblankic model?
HNO3, because it is an oxoacid.
Very good. HCl, binary, hydrochloric. H2S, binary, hydrosulfuric. HF, hydrofluoric. Very good. Now, what is the name of HNO2?
Not hydra, whatever. It's just. Can you give me the polyatomic ion chart?
Yes, here you go. There it is. Nitrite ion, NO2.
Ite. 8 goes to ich, ite goes to ite. Nitrous acid.
Very good. Nitrous acid. HClO4.
ClO4. What's the polyatomic? I'll just look. Perchlorate. So 8 goes to ich. Perchloric acid.
Very good. Perchloric acid. HF.
This is a binary acid. Hydrofluoric acid.
Very good. Hydrofluoric acid. And industrially, hydrofluoric acid is probably the most dangerous acid. Even though it's not a strong acid, it is very deadly. Okay? Whoops. What do we have here? HMNO4.
Permanganate. 8 goes to ich. Permanganic acid.
Very good. Permanganic acid.
Carbonic acid.
Very good. Carbonic acid. So, here's another one. HClO3.
ClO3. Chlorate. Chloric acid. C.
That's right. Very good. So, at home, remember to push pause if you want to test yourself. Why don't you push pause on this one? Test yourself. See if you can find out what the answer is. Okay, very good. Sulfurous acid. Now, let's see how our chemicals that we've been talking about ionize in water. So here is a weak base, methylamine, CH3NH2. How does this ionize in water?
Well, it's not a strong base. I know because it says it's a weak base.
That's right. Very good. It says it's a weak base, so it doesn't dissociate when you put it into water, but what does it do?
It interacts with the water molecule. So we're going to write CH3NH2 interacting with the water molecule.
Like that?
Yeah. Products are, it's a base, so the product, one of them has to be the hydroxide ion.
Very good. It's a base, so we're going to have the hydroxide ion. And then what?
Well, that hydroxide ion was formed by taking a hydrogen away from the water, so the result is CH3 NH3 plus.
Very good. NH3 plus. Very good.
Why don't you put the CH with the N and not with the C?
Well, that has to do with where the hydrogen actually is going. And the hydrogen is bonding to the nitrogen, at least in this case. So in the future, in organic chemistry, we'll talk a little bit more about that. But the hydrogen in a nitrogenous base will always go with the H. Oh, we forgot the double arrow, didn't we?
I was going to tell you, you just went too fast.
Okay, very good. So, let's do now our weak acid, HNO2.
That's easy. Hydrogen ion and the nitrite ion, and then just a double arrow.
Very good. Hydrogen ion and the nitrate ion.
Oh, they included the water molecule. You can do that too. Water molecule, H3O plus.
Right. Very good. So it can be written like that, or it could also just be written HNO2, and we get the hydrogen ion and the NO2 minus ion. Double arrow to show that this is a weak acid. Very good. Now this strong acid?
Same thing, just single arrow. H plus, ClO3 minus.
Very good.
And if you include the water, that.
Yep, excellent. Strong base, strontium hydroxide.
Same thing, strontium ion and a hydroxide ion.
Like that?
Yeah, there's two hydroxide ions.
Very good. Important to recognize, right? Strontium hydroxide, two hydroxide ions. Okay. We call these types of reactions, the ones that we've been introducing to ourselves or teaching about, metathesis reaction, talking about metathesis reactions. Metathesis is also known as double replacement. I'm just trading my reactants, the cation here, with the anion of the other, and the cation with one and the anion of the other. All right? So we're changing partners. And these reactions will only occur if the products, A, D, and CB, are either precipitates, like we showed already, precipitate reaction, or if they are, if they're precipitates, or if they're, well, here, let's go into this one. Reaction will occur if you get a precipitate, right? Or if we're reacting acids and bases, and so we form water, which is a liquid, that's not going to ionize. It's a molecular compound. It's not going to ionize and dissociate in water. Or if a weak electrolyte is changes, like if a weak acid is formed or a weak acid is consumed by a base, or a gas is formed. Now, we're not going to spend a lot of time talking about the gas scenarios, but you want to be mindful that some compounds will kind of release a gas once they're formed or come into solution. Okay, so let's then predict these metathesis reactions by looking at the reactants and then knowing that the products are going to just swap ions, right? So the H here is going to go with the hydroxide ion and the calcium is going to go with the chloride ion, all right? So we can look at the reactants and know that because it's a metathesis reaction, what the products are going to be. If the products don't form either water or a precipitate or a chemical that releases a gas, or if there's no net ionic equation, in other words. I mean, if you don't have a net ionic equation, then we say the reaction won't occur. Nothing will actually happen. Okay? And this is possible because just because I'm combining things together doesn't mean that chemistry will actually occur. Okay. And to predict our whether or not a compound is soluble, whether a precipitate will form, we use, again, our solubility rules. Let's practice our solubility rules here. I'll bring them up. You tell me whether or not these compounds are soluble or insoluble.
Calcium acetate is soluble because Rule 2 says that acetate ions are always soluble.
Very good. Iron carbonate.
Rule 6, carbonate's insoluble. So iron carbonate is not soluble.
Very good. Silver chloride.
Rule 3, chlorides are soluble, but not with silver. It's an exception.
Very good. Excellent job. Oh, I didn't call this by the right name. What is the name for this iron carbonate? It should be called something else so that we know what the charge is on the iron.
Can you show me the polyatomic ion chart? There's the carbonate. Carbonate's a -2. That iron must be a +2. So that's iron 2 carbonate.
Very good. Iron 2 carbonate. Okay, so what are the products? Tell me what the products will be.
The lead is going to go with the hydroxide, and the calcium is going to go with the nitrite. So lead, hydroxide. Oh yeah, we have to put a number with the lead. Lead, let me see, it's with nitrate right now. It's got a +2 charge then. So lead 2 hydroxide and calcium nitrate.
Very good. And whoops, are either of those going to be insoluble?
Let me look at the solubility rules. Oh yeah, hydroxides are generally insoluble. So lead hydroxide is not going to be soluble.
Very good. So then we say, yes, a chemical reaction occurred because we have formed a precipitate. All right, here. what are our products? Let's let the folks at home do this one, okay? Let's let the folks at home do it. Give them a few seconds, push pause so you can work on it, and then we'll show you the answer. Okay, here we go. Hope you got that. Barium carbonate is insoluble, right? Next one, work on this at home. Okay, I'm going to show you now, so push pause if you haven't finished. All right, excellent. Work on it at home. Push pause if you haven't got the answer yet. Okay, I'm going to show you the answer. Okay, so because calcium chloride, one of the products, is soluble, and sodium nitrate is also soluble, then we say that no reaction has occurred. Because if you think about the net ionic equation, if all of these were ionized, and ions were shown on the left and the right, all would be spectator ions. Okay, very good. All right, one more for the folks at home. Work on this one. Push pause now. All right, after you got the answer, here we go. I'm going to show you the answer. 1, 2. Excellent. Good job. Did you get that one, Fred?
I didn't have time.
Okay. All right. All right. Now, neutralization, or also acid-base reactions. These are reactions because, in a way, the water is kind of precipitating out. You had ions, the hydrogen ion and the hydroxide ion find each other and form water. Also, you can have acids and bases coming together to form new kinds of compounds. Here it's an ionic compound, right? So this was a weak base here with a strong acid, and now it's an ionic compound. If you look at the net ionic equation for this one, down here, let's write the net ionic equation. HCl, is that going to dissociate in water?
Yes.
How did you know?
Well, I don't know. I just guessed.
Well, HCl is a strong acid. It's a strong acid, so that's how we know. Did you write the strong acids down?
Yeah. Well, I have kind of trouble writing.
Well, I'll write it down for you later, okay, Fred?
Okay.
So, HCl is a strong acid, and therefore it does completely dissociate into water. Okay? So, HCl should be written like that in the ionic equation. NH3, what kind of a compound is NH3?
Well, it's a molecular compound, so it's not going to ionize, that's for sure. It's a weak base, is that right?
Yeah, it is a weak base, right? We've talked about it a little bit. So now, that NH3 does not dissociate. It's just written like that. But NH4Cl, what kind of a compound is that?
NH4, that's ammonium ion, so that's an ionic compound.
That's right. So we have NH4, and you could look on your solubility rules and see that all salts containing ammonium are soluble. Therefore, that is our equation, and our net ionic equation is that. So because we have a net ionic equation, we can say, yes, some chemistry has occurred here. Okay, here you go. Your turn. Find out what the net ionic equation is for this reaction. All right, and tell me whether the reaction occurs by what the products are. Okay. Push pause and work on it if you haven't done so. Okay, done. Good. So let's see. NH3CN. All right, that's our compound. I'll go over that one. So we have NH3. We already decided that NH3 does not dissociate. HCN. Does that one dissociate?
It's an acid.
That's right, it's an acid, so it should dissociate.
Do you write it as dissociated?
I don't know. How do we know if we write it as dissociated?
You only write it dissociated if it's a strong acid. But HCN is not a strong acid. So no, you don't write it as dissociated.
That's right. HCN. Can chemistry still occur here?
Yeah, NH3 is a base, so it's going to take that hydrogen.
That's right. And we're going to get NH4 plus and CN minus. Very good. Are there any spectator ions here?
No.
That's right, no spectator ions. So that's chemistry. There is some chemistry occurring, and our products, now NH4CN is written as ionized, so it could also be NH4CN like that. But basically both of these are NH4CN aqueous, or A. Okay, another one for the folks at home. Work on it. Push pause, figure it out. Okay, 2 seconds. 1, 2, I'm going to show you. All right, C. So hopefully you were able to write out the reactants completely. HF is not a strong acid. Therefore, it doesn't dissociate, so it's going to be in the net ionic equation. Okay, very good. Here are 3 of the compounds that form gases when combined with water. Here's a couple others. All right, so if these compounds are ever products, then a gas will form. And again, we mentioned that we're not going to really be held accountable for remembering this, but we're remembering these compounds specifically. But there are compounds that form gas when their result is the products, right? And that can be the driving process for some of the reactions. All right, so we can form precipitates, neutralize acids, base, or gas forming. These are metathesis reactions. All right, now we're going to talk about concentration. We said that the amount of solute in solution is the we can tell somebody how much is in solution by telling them a concentration, and that's what we're talking about when we talk about concentration. And there's a variety of ways to express concentration, and in this class we'll talk about some of them. But the most important one that we want to introduce to you is what we call molarity. Molarity. It's a way of expressing concentration. It expresses moles of solute per liter of solution. Moles of solute per liter of solution. So if I say something is 6 molar, and big M is the abbreviation for molarity, and it means, again, moles of solute per liter of solution. Now remember what that means. Solute is the stuff that's dissolved in it, and liters, not of solvent, but liters of solution, right? So 6 molar HCl contains 6 moles of HCl for every liter of solution that I have. Okay? We can identify the molarity of a solution using our dimensional analysis. Use our dimensional analysis. Essentially, to the right of the equal sign, we write molarity. All right? How would I write molarity?
Big M, you said.
Yeah, big M, but I want to be very specific when I write the units over here so that they can be used as a roadmap. So what am I going to write?
Moles per liter?
That's right. And I want to be even more specific. Moles of, in this case, KNO3 per liter of solution. All right? So moles of KNO3 per liter of solution. And then I write my line, right? Give myself plenty of space. What do you think I could start with here?
They gave us 10.2 grams of KNO3 and 350 milliliters of solution.
All right, so now we have to think a little bit. We want the liters of solution on the bottom and the moles of KNO3 on top. So if I start with my KNO3 on top, KNO3, my 10.2 grams of KNO3 on top, then that might be good because my grams of KNO3 will be converted to moles of KNO3. All right? So, what is the, let's get this focus very, okay, what values do I need to convert there? What values do I need to use to convert grams to moles?
1 in the moles.
That's right. And what KNO3? What's the mass of KNO3?
Do you have the periodic table so I can add it up?
Yeah, that's exactly right. You would add up 1 potassium. How many nitrogens?
1 and 3 oxygens.
That's right. Well, it's down here for us, isn't it?
Oh, good. Oh, good. 101.
Very good. 101 grams for every mole. So now I'm in moles of KNO3, which is what I want. And now I just need to go to liters of solution. And I can just put down here the 350 milliliters of solution. And I can go from milliliters to liters by saying there's 1,000 milliliters for every 1 liter. Okay? So I went from grams of KNO3 to moles of KNO3, and that's where I stopped with what's on top. But on the bottom, I took the milliliters and went to liters. Okay, so this is kind of backwards of how we're doing it. We wanted liters on the bottom, so we put milliliters here, and then we got rid of the milliliters to get liters. And you'd say, well, what goes here? Well, you don't need to have something there, right? We're just trying to get the units to look the way we want them to look. Okay, very good. You want to try that second one?
Yeah, I'll do it. Can you write for me?
Yeah, I can write for you.
Okay, let's see. I might need some help. This is kind of complicated.
That's all right.
Equal sign.
Very good. Equal sign. What goes to the right of the equal sign?
Mass of KNO3. Grams of KNO3?
Very good. Grams of KNO3. And you folks at home, you keep trying along as well. Try to predict what's going to happen. Try to write it down yourself. Where are we going to stop with the top? Where are we going to start with the top left?
Oh, I can get, where can I get grams of KNO3? They told me milliliters of the solution. They told me molar solution. I can get it from moles, I guess.
Yeah. Do we know anything about the moles?
We know how many moles there are per liter.
That's right, 0.05. So if I put moles of KNO3 up here, right, are 0.05 moles of KNO3, I know that's how many moles there are per liter of solution. All right, so you see here that we use the molarity in moles per liter as a kind of a statement of our units, and then we'll be able to use other conversion factors to get these moles to grams, right? How do we get the moles to the grams?
The molar mass.
Very good. So moles of KNO3 goes down here, right? And grams of KNO3 goes up here. 101 still, grams per mole. Okay, and now I just need liters of solution. I need to get rid of the liters because I only want grams by myself. How can I get rid of liters of solution?
You got 25.33 milliliters, so you could convert that to liters.
That's right. And if I didn't want to do that in my head, I could go 0.33 milliliters. And then I could go from milliliters to because I need to get rid of liters of solution, right? To liters. So 1 liter is 1,000 milliliters. There we go. So now my moles of KNO3 are gone, and I have grams. My liters of solution are gone, and also my milliliters of solution are gone, which is great, because now I just want grams. Okay, very good. So this one here, we didn't actually solve it with the calculator. Why don't you practice putting that in the calculator and see if you get the right answer. I'm going to show you the answers now. 0.29 molar for the bottom one here. This one here. Why don't you put it into the calculator and see what you get. 0.128 grams of KNO3. Okay, excellent job. Here's another one. 10 grams of sodium chloride are dissolved in 75 milliliters. What is the molarity? Why don't you take a stab at it? I'm going to let you do it. Okay, now I'm going to walk through it with you. Well, here, I'll show you the answer, and if you got it, then you can move forward. Otherwise, I'm also going to walk through it here with people. Tell me, Fred, what goes to the right of my equal sign?
Let's see. They're looking for molarity, so moles per liter.
Don't be chintzy on me. Tell me moles of what?
Oh, yeah. Moles of sodium chloride.
Very good. Moles of sodium chloride. We want that goal to be as clear as possible so that when we're stuck, we know where we're going. What can I start up here?
You put the sodium chloride on top, so 10 grams of sodium chloride.
10 grams of sodium chloride. Whoops. There we go. Then, whoops. It's a little bit too small. Thanks, Fred. Okay. 10 grams of sodium chloride. And now I need to convert that to what?
To moles. 58.
Oh yeah, 58. 58 grams for every 1 mole. So I'm in moles of sodium chloride. So what do I need to do now?
Just get the liters down there.
Okay. What do we got? 350?
No, 75.
75 milliliters?
Yeah, which you can do that in your head. It's not that hard. 0.075 liters.
All right. Very good. So our 10 divided by 58 divided by 0.075 should be our 2.28. Okay. Very good. Now we're going to talk about dilution. Dilution is something that you need to be able to understand for the rest of your life, because sometimes you'll find yourself at the most important event in your life and things will be rough. What am I talking about, Fred?
I have no idea. What are you talking about?
I'm talking about parties.
What?
Yeah, remember when you go to a party, what's the most important thing to find out at a party to see if it's a good party?
If your friends are there?
No, it's the punch. It's about the punch.
What? The punch? What do you mean?
You know, the juice that you drink at the party. If the juice is good, you know the party's good.
I've never heard of that.
Well, if you go to a party and the punch is too sweet, right, you know that the party wasn't made by a chemist, right? If the punch is too sweet, what can you do to fix it?
I guess you can dilute it.
That's right, dilution, right? You can dilute it. And we need to be able to dilute our punch always, and we always need to be able to have a way to regurgitate this, what we call dilution equation, okay?
I'll just memorize the equation.
That's fine, but you're going to come upon the day when you don't have it memorized and need it. So you need to be able to regurgitate it.
What's regurgitate mean?
Well, I'll let you look that up on the internet. But essentially, what you're going to do is kind of bring it up from nothing, okay? And this is how you do it. You remember your experience at the party. I'm going to bring out different colored pens, all right? So I'm at the party. Here it is. Here I'm at the party. I got my cup of punch at the party, okay? But the punch is too concentrated, too sweet, all right? And I want to dilute my punch. How do I dilute my punch?
Add water.
That's right. I add water, and that will dilute the punch. Now, let's say I want the punch half as concentrated. Then how much water do I have to add?
Half as much.
Half as much? What do you mean half as much?
Well, no. If you want it half as concentrated, you add the same amount of water as you have punch.
That's right. That's right. So if I want to dilute my punch to half its concentration, I'm going to have to add an equivalent amount of water, and then in the end, I'm going to have less concentrated, but more punch, right? How much more?
Twice as much punch you're going to have after you dilute it.
Very good. So you have that memory. Have you done this before, Fred?
I actually have.
Oh, you have?
Yeah, I did it just the other day.
Very good. So you have a lot of experience diluting punch to make it half as concentrated. Now, did you think about the concentration of your punch before and after?
I don't know.
All right. Let's put some numbers in here so we can quantify what's going on. Can you tell me, for example, what the concentration of this punch is?
I don't know this concentration.
Come on, Fred, be creative. Just come up with some number.
12?
Okay, 12. Very good. So we'll call it 12. Now, it could be molar. Call it molar. That's fine. 12 molar is the concentration. What's the concentration of this punch over here?
It has to be 6.
That's right, 6 molar. It's half as concentrated. Now, how much punch do I have here, Fred?
I can't tell.
Make it up.
Okay. You have a cup?
Well, let's use milliliters.
Okay. 100 milliliters?
All right, 100 milliliters. What is the volume of this over here then?
200 milliliters.
200 milliliters. Very good. So with this information, you know that there's some sort of relationship, and you can see it, right? 12 is twice as much as 6, 200 is twice as much as 100. So you can see that there's some relationship, and it will allow you to use the information. This we call our initial concentration. This we call our initial volume. This we call our final concentration, and this is our final volume. All right, so you can use those values there, this regurgitated experience, to remember what the dilution equation is. And you play around with those numbers, and you'll get some form of this. You know, and this isn't the only way that it can be. C1V1 over CFVF. Or sometimes they say C1V1, C2V2, which is fine. But essentially, your initial concentration times your initial volume will equal the final concentration times your final volume for any dilution that you make. Okay? Now be careful. This isn't necessarily saying that anything about the amount of water that you need to add to these. You see that? But it's implied in there, and you can figure it out easily. So we're going to use this the dilution equation, C1V1, C2V2, or CIVI, CFVF, to solve some problems. Okay? Dilution allows the molecules to move around more, right? There's more water compared to the amount of solute that there is. There's more solvent. Dilution in the lab is done very quantitatively. We have to know exactly the volume of material that we're using initially, and exactly know the final volume, right? And once we do that, we can know the final concentration. So here's a question. What volume of 12.1 molar HCl are needed to create 250 milliliters of 3.2 molar HCl? The only problem with these questions is kind of thinking, what's C1, what's C2, what's V1, what's V2? All right, and in this case, our initial concentration, what do you think?
Looks like the 12.1.
That's right, 12.1 is our initial concentration. Our initial volume, right, because we're looking for this.
It doesn't say.
That's right, C1V1 equals C2V2. So our initial concentration.
It doesn't say our initial volume. It says initial concentration is 12.1.
All right. So C1, 12.1. V1, we don't know. Okay. Type it up above, or write it up above here, 12.1. X.
Final concentration is 3.2. And final volume is 250 milliliters. Does that have to be in milliliters, or can it be in liters?
Well, whatever the units are over here, the same units will be over there. So it doesn't matter really what units you have. Just recognize that you do have to use the same units on the right and the left. All right, so putting that in the calculator, 3.2 times 250 divided by our 12.1, and our answer is 66. So what is that answer?
66.
But I mean, what is it? 66 what?
66 milliliters of the 12.1.
Very good. And how much water do we add?
250.
No. 250 is what?
250 is the final volume. Sorry.
That's right. 250 is the final volume. So if we had to have 66 milliliters of the 12.1, how much water would we have to add?
Just 250 minus the 66.
That's right. Very good. Okay. Next one here. I'll let you folks at home try this one. See if you can get it. All right. 1, 2. I'm going to show you the answer. Push pause if you don't got it yet. 0.3 molar. 0.3 molar. Very good. All right. 20 mils of 3.11 molar HCl are added to 15 mils of water. What's the resulting concentration? All right. You guys try this one at home, but be careful. There's a trick here.
Doesn't look that hard.
There's something tricky.
I'm going to do it in my paper, okay?
Yeah, you go ahead and do it.
I guess I don't have access to my hands right now. Can you help me out?
Yeah, I can help you out.
Just write what I tell you.
Okay, I'll write what you tell me.
20 times 3.11 equals 15 times x. Okay, so I got x being 4.15.
All right. Does that sound right?
Yeah, 4.15.
But why is it when you took 20 milliliters of 3.11 molar, that's your initial volume of your initial concentration, you ended up with a higher concentration when you added water?
4.15. Yeah, what's wrong?
Well, why did you use 15 as your V2? This is your V2, right?
Yeah, so that's a V1, that's C1, that's V2, and that's supposed to tell me C2.
Okay. But why did you use 15 for your V2?
Oh, 15 milliliters of water was added, so V2 should be 35.
Very good. So V2 should be 35. So that's not going to be 4.5. That's going to be our 1.77. Okay. Very good. Did you see the little trick there?
Yeah, that was tricky.
It's not too tricky though, right? So we should be able to read it and recognize that when they say water added or how much water is being added, needs to be added, because that's what they want to know often. All right. So we should be able to see through that now. All right. Using the solution stoichiometry, we can answer so many different problems now that we have an understanding of concentration. We have an understanding of the equation stoichiometry, right? There's all sorts of different things we can calculate given the information that we know now. So, like what volume of 2 molar HCl is needed to react 25.2 grams of sodium carbonate completely?
That is a crazy question. I have no idea.
Perfect. We've arrived. We've arrived, Fred. We've gotten to the point where our tool has to see us through. Our tool has to see us through. So let's see if we can use our tool, Fred.
Okay, write an equal sign.
Very good. Equal sign. And write it all the way to the right. And then what units are we after?
Volume. Milliliters?
Okay, can we do liters?
Yeah, sure, liters.
Liters or milliliters, you know, in the end we can convert that pretty well in our mind. And then we draw a line. Now this is also a good time to breathe out slowly when you draw that line so that you get out the bad air. Loosen up a little bit. Okay. Good. Okay. So what's next?
25.2 grams of sodium carbonate.
All right. Let's see if that works. 25.2 grams of sodium carbonate. I need 2 CO3. Then what?
I guess we go to moles of sodium carbonate.
Good. It's always good to go to moles. Go to the land of the moles. Grams of sodium carbonate to moles of sodium carbonate. They gave us 106. That's nice. 106 grams per mole. Now I'm in moles of sodium carbonate. What am I going to do now?
Well, we're reacting the sodium chloride with the sodium carbonate with the HCl, right?
Yeah.
I think we need an equation.
I think you're right. I think we need an equation. Can we get that equation?
I don't think so because we don't know how to do this.
Yeah, we do. What are we combining?
HCl and sodium carbonate.
Well, let's do it. If I have Na2CO3 reacting with HCl.
Oh yeah, we can do this.
What are our products?
NaCl and HCO3.
Like that?
Yeah, but it's not balanced.
It's not balanced. And I think there's also another problem.
What? What's wrong with it?
Well, carbonate ion is a -2 charge.
Oh, yeah. So I got to pay attention to that. H2CO3.
Very good. Okay. So, is it balanced now?
No, it's still not balanced. You need a 2 in front of the sodium chloride.
Here?
Yeah. That's... Oh, 2 in front of the HCl, too.
Is that balanced?
Yeah, that's good. And now we got an equation, so I can relate moles of sodium carbonate to moles of HCl.
Very good. So I can go now from moles of sodium carbonate, like we did before, go to moles of HCl. All right? What's the ratio?
2 to 1.
2 HCl's to 1, like that?
Yeah, that's right.
Okay, now I'm in moles of HCl, but I need liters. Oops, we weren't very good right there. That's liters of HCl, right?
Yeah. So moles of HCl to liters of HCl. We need moles on the bottom for sure.
Good point. Moles of HCl need to get rid of moles, and somehow we need to get it to liters. Do we know anything about the relationship between the moles of HCl and the liters of HCl?
I don't.
What's the molarity mean?
Oh yeah, that's what molarity is. It's the relationship between the moles per liter of solution. So you can put 2 moles of HCl,
This?
yeah, per liter. Very good. So we got it. We're in liters of HCl.
All right. Excellent job. So we're in liters of HCl. Moles cancel out. Moles of sodium carbonate related to moles of HCl. And then grams of sodium carbonate. Excellent job, Fred. So we got 25.2 divided by 106 times 2 divided by 2. And that should be my liters of HCl. All right. 0.238 liters of HCl. 238 milliliters.
Told you we should have been in milliliters.
Oh, yeah. We're a little bit better. Okay. Here's another one. How many moles of barium sulfate will form if 20 mils of 0.6 molar barium chloride is mixed with 30 milliliters of 0.5 molar magnesium sulfate?
Oh, brother. That's a hard one. I need to take a nap.
Come on, Fred. You can do it.
Okay. Well, where should I start?
Well, we know what's to the right of the equal sign.
Oh yeah, that's easy. Moles of barium sulfate.
Very good. Moles of barium sulfate. All right. So, moles of barium sulfate, equal sign. Very good. Okay. Now what?
If you start off with the barium chloride, maybe? I think I want an equation.
Yeah, let's get an equation. That's a good idea. So what are we reacting here?
How many moles of barium sulfate will form? Barium sulfate's a product.
Okay, I'll write that down here to the right of the equal sign. Or it's not right of the equal sign, but right of the arrow.
Barium chloride aqueous and magnesium sulfate aqueous.
Yeah, those are our reactants, right? Barium chloride and magnesium sulfate. Okay. What's our other product?
Magnesium chloride.
What's the chemical formula for magnesium chloride?
Oh, can you give me the periodic table?
Yeah.
Mg, second column, so that's +2, so there's 2 chlorides. So magnesium, MgCl2.
Okay, very good. So, is this balanced?
No. Well, yeah. Yeah, it is, actually. 1 barium, 2 chloride, 2 chloride, 1 magnesium, 1 magnesium, 1 sulfate, 1 sulfate. So, yeah, it's balanced.
Okay, very good. So now we have our chemical reaction. We can go to the land of the moles and get the power of that equation anytime we want to. Okay, so we're after moles of barium sulfate, and we can start with what?
I guess barium chloride, 0.6 moles per liter of barium chloride.
All right, 0.6 moles of barium chloride for every 1 liter of solution. Is that okay?
Yeah. Now I can go to moles of barium sulfate because I have the equation.
Very good. Moles of barium chloride, moles of barium sulfate. And look, that's what we want, moles of barium sulfate, right? So what's the relationship?
1 to 1.
Very good. 1 to 1. So 0.6 moles of barium sulfate, we got barium sulfate on top, per liter of solution. How are we going to get rid of liters of solution? Because we don't want liters of solution.
Use the volume of barium sulfate, the 20 mils of barium sulfate.
Yeah, 20 mils, 20 milliliters of barium sulfate. 1 liter is 0.6 molars. So that's 0.02 liters. Is it okay if I just convert it like that in our head?
Yeah, that's fine.
0.062 liters of our solution of barium chloride. All right, we got it. The liters cancel out. And so then we're just left with moles of barium sulfate. 0.6 times 0.02, and that's it. That tells us how many moles of barium sulfate. Why did they give us so much information?
Yeah. They told us about magnesium sulfate as well. Oh, wait. They told us about magnesium sulfate as well.
What's that mean?
This is a limiting reagent problem.
Oh, good, good. You caught it. This is a limiting reagent problem because they've told us about the contents or the concentrations, the amounts of 2 of the reactants. So I can do this, but I also have to repeat it, right? Do it again a second time, in which I am solving again the second time for the moles of barium sulfate. But this time I use what?
Magnesium sulfate.
All right. So what do I put here?
0.5 moles of magnesium sulfate per liter of solution. And then let's get rid of those liters first.
Okay, you want to do that first?
Yeah, 0.03 liters of the solution.
Like that?
Yeah. Then we can go from moles of magnesium sulfate to moles of barium sulfate.
Is that 1 to 1?
Yeah.
Okay, so 0.5 times 0.03. So 0.5 times 0.03, that's 0.15. The other one is 0.6 times 0.02. That's 0.012. Well, this is 0.015. 0.015 and 0.012. So that means 0.012, because it's the smallest one, right? Lowest amount, is going to be our answer. And that means barium chloride is what?
Limiting reagent.
That's right. Barium chloride is our limiting reagent. So we're actually only going to get our 0.12 of barium sulfate. Fabulous job, Fred. We're learning how to learn, even though we don't know how to do it. Good. Here's another one. What mass of sodium carbonate can be neutralized with 25 mils of 3.11 molar HCl? All right, we're going to give the folks at home a chance to do this one. Okay, you got it? I'm going to give you the answer. 4.12 grams. Okay, so let's show them how to do it, Fred. What goes to the right of the equal sign?
Grams of sodium carbonate.
Very good. Equal sign. Grams of sodium carbonate. Na2CO3. We'll start with what?
Start with 3.11 molar HCl.
Okay, very good. Now, sometimes people will start with other things, which you can get to the right answer. If you ever are working and you find out that your units are not getting you where you want to go, what do?
Start over.
That's right. You can always start over. It takes a little more paper, but the paper is here for us to learn. So we don't want to say, I'm not going to start over. I'm going to fix it. Just start over. Okay? So 3.11, what are the units?
Moles of HCl.
Like that? Is that it? Yep.
Yep.
Almost. What do we have to have down here?
Oh yeah, per liter of solution.
And then how many milliliters do we have?
25, but that's 0.025 liters of HCl.
Very good. So we got it already, moles of HCl. So then we can go from where?
We need to get to grams of sodium carbonate. So moles of HCl down below to moles of sodium carbonate.
That's right. What's the ratio?
We don't have an equation.
That's right. We got to do an equation, don't we? HCl, Na2CO3, products.
NaCl, H2CO3. We just did this one.
That's right. H2CO3. And then it was 2 and 2, right?
Yeah. Okay, so it's 1 to 2.
Very good. 1 to 2. So 3.11 times 0.25 divided by 0.2. Is that right? Moles of HCl is gone. Liters of solution is gone. I'm left with, oh no, I'm not done yet, am I? Because I'm left with moles of Na2CO3. Now I need to go from moles of Na2CO3 to what?
Grams.
That's right, grams of Na2CO3. And how many grams is it?
106.
That's right, 106. They gave it to us up there, right? All right, so that should be it. Moles is gone, and I'm left with grams. Very good. You see how I caught myself? I could double check because I had my correct units that I was after here, and I could see where I was going to end up if I had just stopped right there. I don't even need to put it in the calculator. I trust that you can get that part done. Okay. We can do the same thing with concentrations of ions. And we mentioned before that concentrations of ions is important. So let's do a couple of problems where we look at the concentrations of ion. What's the concentration of chloride ion in 0.6 molar barium chloride? Well, 0.6 moles of barium chloride for every liter of solution, but there's 2 moles of chloride ion for every mole of barium chloride.
So you just multiply it by 2.
Don't say that. Don't say that, right?
Oh yeah, sorry.
Yeah, no, that's right. But we want to make sure we set up our system so that we can always answer our questions well. What volume of solution containing 0.5 molar silver ion will be required to react 100 milliliters of 0.0075 molar chloride ion? Well, I think we're going to let the folks at home tackle this one, don't you think?
Yeah, sounds good.
It's a good learning experience too, right? Good opportunity to learn. Equal sign on the right, volume of solution, volume of our 0.5 molar, so milliliters or liters on the right of the equal sign. Start with point. So what volume of solution? This is kind of tricky because we need to have liters of our silver chloride solution on top. So we're going to put 1 liter is 0.5 moles of silver ion. And then we're going to react 100 milliliters of 0.0075 moles of chloride ion.
That's a tough one.
All right, did you try it? If you tried it and you didn't get it, try it again, and then we'll work on it together. Okay, here we go. Equal sign. To the right of the equal sign, I'm going to put liters of our silver ion solution. Okay, liters of our silver ion solution. And then what should I start with top left?
Can we start with the 0.075 molar chloride ion?
Yeah, we can do that. There's a lot of ways you could start here. 0.0075 molar chloride ion. Sorry, we don't want it that way. We want moles for every 1 liter, right? That's always how I do it.
Yeah. Okay, then go from moles of chloride to moles of silver.
Okay, so we want liters of our silver ion solution. We got moles over here.
Well, you know, they gave you the molarity, so you can go from moles to liter.
All right, moles of silver ion to liters of silver ion. Is that it? Our moles of chloride ion cancel out. Moles of silver ion cancel out. We're left with liters of silver ion. Oh, but we have liters of the chloride ion solution.
But you can get rid of that with 0.1 liters of the chloride ion solution.
Yeah, they said 100 milliliters of the chloride ion. So that's 0.1 liters of my chloride solution. So this is the chloride solution here, right? Okay, so is that it?
Yeah, I think so.
All right, so now I think that there's a likelihood that some people started with the moles of silver ion up top. But that would still be okay, because you could start with this and then convert it to moles of... Oh, no. If you started with moles of silver ion on top, that wouldn't work, because see, the molarity here has to be liters over moles, so that you get liters on the top here. So this is an example of a problem where people probably started in the wrong spot and couldn't get the answer. Oh, we didn't talk about this, did we?
Oh, yeah.
But we needed to recognize that silver chloride was a 1-to-1 ratio, so this is going to be 1-to-1. Okay, very good. Now I'm going to introduce you to an idea or a type of experiment called a titration experiments. A titration is just a chemical reaction, a controlled experiment where we react reactants and products or reactants together in a controlled way, and we have what's called an indicator to tell us that the reaction has come to completion. So we have a titrant that is the one that is known to a titrate. No, sorry, titrant is the one that's unknown to a titrate, which is our concentration of our unknown. And we come to an endpoint, meaning that the reaction has completed. There has to also be what's called an indicator. So for a titration to work, you need a known, some solution that you know the concentration of, an unknown, and then you need some sort of indicator to tell us when we've got to the endpoint. But then you also want to have the chemical reaction so you can use the stoichiometry to predict how much was in your unknown. We typically use burettes for this sort of thing, and we use a dye as an indicator, a pH indicator, for example. That way, the pH will be one color when it's acidic, and it'll change when it becomes basic. And so that'll tell us when the reaction has finished. The burette allows us to see exactly how much volume we've delivered, and from that we can identify how much of our unknown titrate, right? So titrant, A-N-T, is what we know, and the titrate is what we don't know. It doesn't necessarily have to be that way. You can always flip it around in terms of what's being added to what. It's the same thing. Okay, so let's see if we can solve a problem. It's basically the same thing, but they will have the word titration in there. And so you have to make sure you're familiar with that word. So 25 mils of HCl titrated with 75 mils of the 1.3 molar calcium hydroxide. What's the concentration of the HCl? So, Fred, help me out. What goes to the right of my equal sign?
Concentration of HCl. What's that? Molarity?
That's right. Molarity. Now, do I want to write big M HCl?
No, write moles of HCl.
Like that?
And then over 1 liter.
Very good. That separates those units out, gives us our goals. We know what we're looking for. Where should I start over here?
25 mils of HCl?
Well, could, because it's the first thing that they give us. However, can we see that we want our liters of HCl to end up on the bottom? So that'll probably end up on the bottom somewhere. We could start it right on the bottom. It doesn't matter. But we need to get moles of HCl. Let's concentrate on getting the moles of HCl on top first.
Well, they gave us the moles of calcium hydroxide.
Yeah, from the moles of calcium hydroxide, we can relate that to the moles of HCl, calcium hydroxide, 2 hydroxides. Okay. If I go from moles of calcium hydroxide to moles of HCl, I'm going to need a what?
An equation.
Yeah, I'm going to need an equation. Do you know that equation?
No, but you can do it.
Yeah, so HCl plus what?
Calcium hydroxide.
What are our products?
Calcium chloride?
Very good. Like that?
No, 2 chloride.
Okay, good. What's our other product?
Water.
That's right, water. Is it balanced?
No.
What needs to happen?
2 HCl's.
Like that?
Yeah, and I guess 2 waters at the end. Okay, so what's next?
Well, we got it balanced, and so now we can see that the ratio of moles of HCl to moles of calcium hydroxide is there for us. What is it?
2 HCl's for every 1 calcium hydroxide.
Very good. 2 to 1. Excellent. Now I have moles of HCl on top, right? All done with the top. Now I just need the liters of HCl on the bottom. Do I know how many liters of HCl? Oh, wait. This isn't 1.3 moles, is it? It's supposed to be 1.3 moles for every 1 liter of the calcium hydroxide solution.
Oh, okay.
Yeah, because they gave us the 75 mils of the calcium hydroxide solution, so had to probably use somewhere. Now we know. Yeah, because that's not 1.3 moles, it's 1.3 moles per liter. All right, so we're in liters of HCl on the top, that's fine, but now we got to get rid of the liters of calcium hydroxide on the bottom. And we can do that by doing what?
Using the 75 mils.
That's right. 0.075 liters, is that okay, of the calcium hydroxide solution?
Okay.
So there's a calcium hydroxide solution gone. Then what?
Now, we just need liters of HCl on the bottom.
That's right, just need liters of HCl on the bottom, and how many do we got?
0.025.
0.025 liters of HCl on the bottom. This is gone with that there, right? Okay, very good.
Yeah. Put it in the calculator and see what we get.
Okay. 1.3 times 2 times 0.075 divided by 0.25. 0.025, sorry. 7.8. What's the concentration of the HCl? 7.8 molar. Fabulous job.
Yeah, we got it.
Good job. Okay, here's another one. Give you guys a chance to work on this one at home. All right, a sample of a metal ore is reacted according to the following reaction. If 25 milliliters of 2.3 molar HCl are used, what mass of iron is in the sample? So essentially, we have ore, O-R-E, which means a rock or a material, soil, dirt, whatever it is, sample, which is rich, lots of a given element. In this case, it has some iron in it. So we're trying to find out how much iron. So try that one at home. See if you can get it. See how far you can get. Great example of a problem that's kind of different. Haven't quite done it all, but we've done ones like it. So give it a shot. Okay? Push pause. All right, so here we go. 25 mils of, or what mass of iron is in the ore, right? That's what goes to the right of our equal sign.
Yeah. Grams of iron.
That's right. What do we start with?
you can use the moles of HCl because they're going to react with the iron, I guess. That's what. Well, I don't understand the equation. Where's the HCl at?
Yeah, so the equation here is the net ionic equation. So we have the iron ion interacting with H plus ion. Where do we get the H plus ion? I don't know. It's from the hydrochloric acid. It's from the HCl, right? Now, if as I'm explaining this, you say, oh, I get it, and you start thinking, I want to try to solve it for myself, that's what you really should do. You need to learn how to solve these on your own. So you can always push pause and stop and move forward. But the moles of HCl will be equal to the moles of H plus ion. Okay, so if we start off with our 2.3 moles of HCl for every 1 liter of our HCl solution, right? And then what?
Well, you can get rid of the HCl solution.
That's right. I can get rid of this HCl solution because I know that I use 0.025 liters. Is that okay? I converted that 25 mils to 2.5 liters of the HCl solution, right?
Yep. Now you got moles of HCl, which you can convert to moles of iron.
Very good. Moles of HCl. How about if I did this? Moles of H plus ion for the folks at home.
Oh, okay, sure.
Yeah, that way we can see that the moles of HCl, each one has 1 mole of H plus, and then I can go from moles of H plus to moles of iron, and that's 2 to 1. Good. Now I'm in moles of iron, and what do I got to do?
Just go to grams.
That's right, moles of iron to grams of iron. All right, what's the molar mass?
Is it 56?
I don't know. Bring up that periodic table.
55.847.
Oh, good guess, Fred. 55.8 grams for every mole. All right, did we get everything in there? Moles of HCl are gone. Moles of H plus went to moles of H plus. Moles of H plus go to moles of iron. Moles of iron go to grams of iron. So I'm left with grams of iron, which is what I want. I use my moles of HCl. Okay, should be the right answer. All right, 1.6 grams of iron. Excellent. Here's another opportunity for you. I'll let you guys do this one. Push pause, take a stab at it. Okay, carbonate content in a rock determined by titration. 12.5 milliliters of my 3.5 molar H2SO4 are required to titrate the carbonate in the rock, and we want to know the mass of the calcium carbonates present in the sample. Okay, so grams of calcium carbonate is what we're after. True, mass of calcium carbonate, so grams of calcium carbonate. Excellent. So, how are we going to get there?
We have an equation. We put some H plus ion that comes from the acid with the rock, and it eats up the carbonate, apparently. CO3 2 minus plus the 2 H pluses, right?
That's right. Good. So, if we start with the acid, 3.5 molar HCl, that'll relate to the moles of the carbonate, and then we can relate that to the grams of the calcium carbonate.
Okay.
So, what goes here?
3.5 molar H2SO4.
3.5 moles of H2SO4 for every 1 liter of the H2SO4 solution, right? H2SO4 solution. Whoops. Okay. And now I'm in moles of H2SO4. And for the folks at home, I'm going to go to moles of H plus ion. Right?
Okay.
Because it says H plus ion in the equation, right? We see H plus ion in the equation, right?
Yeah.
All right. So what's the ratio? How many moles of H plus to moles of H2SO4?
1 to 1.
Not quite. See H2SO4?
Oh, yeah, 2 to 1.
Yeah, 2 moles of H plus for every mole of H2SO4. Now what?
Moles of H plus to moles of carbonate.
That's right, moles of carbonate. And I can do that because we have the information in the chemical reaction there. What are our stoichiometry?
Carbonate's 1, H plus is 2.
Very good. 1 to 2. Moles of carbonate, what do I do now?
Go to grams of carbonate?
No, I don't want grams of carbonate over here. I want grams of calcium carbonate.
I don't know then.
Well, I can go from moles of carbonate to moles of calcium carbonate.
Oh, yeah, okay. All right, then that's 1 to 1. And then you can go from moles of calcium carbonate to moles of grams of calcium carbonate.
Very good. You know the molar mass?
They gave it to us.
Oh, yeah, 101. No, 100. Did I really get it? Moles of H2SO4. Moles of hydrogen. Moles of carbonate. Moles of calcium carbonate. Grams of calcium carbonate is where I want, but I didn't get rid of this one here, the liters of the H2SO4. So I need that up here to get rid of liters of the H2SO4 solution. Did they tell us information about that?
Yeah, 12.5 mils or 0.0125 liters.
0.0125 liters. Got it. All right. So hopefully that equals our 4.38 in the calculator. Okay. So a little cartoon now about the titration, how titrations occur. All right. This is an example of a titration reaction. We start off here with a weak acid, acetic acid. And it's a weak acid, therefore a small amount of it dissociates, right? If we plot the pH, which we start off here about 4, as we add hydroxide ion, all right? When we add hydroxide ion, it's going to be in the form of aqueous sodium hydroxide. The hydroxide ion itself is going to interact with the hydronium ion and form water. And now there's no acid in this solution. We just neutralized it with the hydroxide ion. But what's going to happen is the carbonate here, the acetic acid, is going to shift its equilibrium because there's nothing here and dissociate. And so we started with an amount of this H3O plus, and we added the sodium hydroxide, and it removed it, but then it redistributed and dissociated more, so we didn't really change the amount of the H3O plus ion very much. And that's reflected in the pH. pH is a measurement of hydrogen ion, or a measurement of hydronium ion. pH stands for the negative log of the hydrogen ion, and we'll talk more about acids later in the chapters. But the pH doesn't change a whole lot even after you added sodium hydroxide. In fact, you can keep doing that. You can keep adding sodium hydroxide, consuming the acid that's there, and more acid will dissociate. And the pH will not change very much. The pH will only change gradually as more hydroxide is added. All right? And this continues, the process continues, again, with the pH not changing very much, until at some point what happens is the hydrogen ion concentration, the acid concentration here begins to get low. And when the acid runs out, right, eventually there's no more acid to dissociate, and so we add more sodium hydroxide, the acid is consumed, and there's no more weak acid to dissociate, and so you get a strong shift in the pH, If we add any more sodium hydroxide, the shift becomes even higher, and you get this sigmoidal curve in your titration curve, which is showing you right at the steepest part of this curve, that is the end point of your reaction. So a nice, easy way to monitor titration, acid-base titration. Not all titrations are acid-base, but initially when we present titrations, it's usually about acid-base. You can monitor the pH. And the steepest part of this titration curve is what we call the end point of the reaction. This point down here, where we were halfway through, now let's scoot back, whoops. Get down here, get back to that slide. When we were at this point here, excuse me, when we were at this point here, we were in what's called the buffer zone of the titration. Here in the buffer zone, if I add more sodium hydroxide, like I had been, the pH doesn't change much because we have more dissociation. But likewise, if I were to add not sodium hydroxide, but HCl, acid, H plus ion, it would associate with the acetate ions that are floating around, and they would shift over to acetic acid, because acetic acid is a weak acid. So if there's H plus ion around, then these are going to suck it up really quick. And so the pH wouldn't shift either. In other words, in this region here, if you add base, the pH doesn't shift. If you add acid, the pH doesn't shift much. And so we call that a buffer zone, a buffer zone. And buffers are very important in chemistry, specifically biochemistry. All right, very good. So a few wonderful facts about titrations. Okay, see you next time.